Okay, Assalamualaikum and good afternoon to everybody, especially for the participants who are involved with this international conference on trends in technology, business, education, and social research. And today, I would like to present my works. Okay, and the title is here, the analysis of fully saturated and soaked soil shear strength in Cameron Highland slope profile. And this is my name is Basharudin bin Abdul Hadi. I also have the team member, Associate Professor Dr. Muhammad Jamal bin Makno, TSIR Anand Rahman, IR Zulfarul Zakaria, Dr. Anas bin Ibrahim, Dr. Nur Aminin, and lastly, Mr. Juhaizat Ahmad. Okay, next. So again, this is my full title. So our highlight now is about the normally engineer understand this one, fully saturated soil, shear strength. They understand this one. But here we included a new one, we call it soak. We're soaking the soil even though it's full saturation for the 7 days, and we see what happened. Is it either the shear strength in terms of P angle going up or going down? We say that it's going down. Is it right? We must prove through laboratory testing. Right. So next, we have number one to determine the classification of soil based on PSD. So we want to identify what the compound of the soil in the Cameron Highland, and this soil sit on the slope. And number two is to characterize the shear strength, behavior of granitic residue soil. Yes, engineer know it, and we are trying to demonstrate about how we are doing a soaking in 7 days. What happened? Right? And the third one, to analyze the effect of fully saturated and soaking soil in slope analysis. We want to see that is it the soaking effects, the slope analysis. Is it any significant different? Alright, for the objective number one, again, using PSD. Alright, first of all, this is, we call it our site location. This is the map of Peninsula of Malaysia. You can see this one is Cameron Highland. And you can see that this color is something like maroon color. So maroon color here indicate is residual sedimentary rock soil. Okay, this is Cameron Highland, because this soil come from the weathering process of granitic rocks. Alright, so when we come to this, this is actually how we want to make a sample in undisturbed sample, where we have, we call it mallet hammer. This is our hammer, and this is our sampler. We put it our sampler, and this one is after finish we take the sample and we wrap it, put it in the box, and then bring back by car to the laboratory. Okay, next. So this is the results. You can see that percentage of the passing, and then we can see that the particle diameter. You can see that this one is 6 sands, gravel classifications, and you can see that the British standard sieve. So what in the size in mm? Then what you can see that actually is very danger, where slope in Cameron Highland 44% is very gravel and very dominant, and then is a 36.47, mean that when the rainfall come in, the gravel and the silt will passing through the water going down and makes this soil become wet and the slope going to fail. Right. Next, we are mapping this slope by using a contour, and this contour we made it by application of theodolite survey. Then when we finish, we get the contour. We cut this section because this one is a very steep one, and we get this profile. And this profile is based on this section. Okay, we call it section AA. Section AA. So this is the profile, and we finish for the objective number 1. Objective number 2, we characterize the saturated, we understand about the civil engineer, and we illustrate the effect of soaking based on saturated shear strength behavior. Right? So this is, we call it the apparatus we rely on. We call it consolidated grain triaxial test on saturated specimen. And look up, this one is, we have a rubber band, and inside the rubber band is the Cameron Island soil. We put it over here, undisturbed sample from Cameron Island, and we test already based on PhD. We have many gravel plus sets. All right. So we want to know now to quantify the physical properties of this soil. This is really important. Okay. And then we control about cell pressure and pore pressure to make sure our soil in the condition where at 1 meter. So 1 meter we time by 9.21. We said it 10. So in 1 meter of soil, so the cell pressure give to the soil sample is 10 kPa. If we call it a 10 meter, okay, for example that this one is the slope, and you can see that this one is the depth is 10 meter. So the soil sitting here, so 10 meter times by the depth, 10 by, we call it gravity, we call it 10, so we get it 100 kPa. So how to do the 100 kPa? We control this one, cell pressure, 100 kPa. So we make sure that this one is 100, this one is 100. Triaxial around the soil sample is 100 kPa. If the soil sitting under the slope is 10 meter. Okay, this is about cell pressure and pore pressure. Right, and we can get, we call it this, after finish, we plot this one. So for the saturated specimen, so we have a demonstration here that's you can see that effective stress is 49.5 kPa here, 49.5 kPa. So you can get around 50 kPa. So Q maximum is you can get 107.1, and you get, we call it effective stress, under effective stress 99.7. So this one, so you get the maximum QU is 202.0 kPa. And the third one is the pressure is around 200 kPa, this line. So you get the reading of maximum derivative stress and axial strain is 293.1 kPa. Until you finish at this one, the effective stress is around 400 kPa. Alright, the reading is 497.6 kPa. Alright, for the derivative stress. And axial strain, you can see that for the axial strain, you can see that is a very correspondent, where you can see that if you have this value 50 kPa, QU is 107, so your axial is around 4.0% of axial strain. So this one is the physical property for the fully saturated of soil. Next, what we have. So we have 7 days soaking. You can see that the value is different, is something like 45.8 kPa about effective stress, this line. So you can get Q is around 100.3 kPa, a little bit lower. Because we are doing a soaking, right? Soaking. We allow water for 7 days. It's never stop. All right. Something like we are simulations 7 days in a heavy rainfall. Okay. So you can see the effective stress 94.16 kPa this line. So you can get around Q maximum about the water stress is 176.4 kPa, and we call it the exit strain is around 8%. So how this one is how you interpret this, and you can see that a little bit Q maximum reading compare it to the fully saturation. So 7 days soaking give you Q maximum or the water stress is quite lower. Alright, so if you compare all this reading to the existing one, to this reading, okay, it show that this one is higher and this one is a little bit lower. And if you go, we call it the curvilinear shear strength envelope. You can see that we had normally we focus on this one because this is the line from the more column. Then we make it straight line and we measure this angle, we get 20 degree. But this one for full restoration. However, for the 7 days soaking, you can see that 70 mean that from 20 degree or P angle, this one we call it P angle. So it's going down to the 17 degree. So mean that you are lacking about 3 degree in 7 days. And if this graph is going to lower and going to lower, this one is mean that the shear strength reduces, and this one we can see danger for slope failure. Alright, next. So this is how we can see this one is 20 degree, 70 degree, and we have data also to support you about the 21 day is 50 degree, 28 days is still going down to the 30 degree. And constellation drain test, we are measuring this one. And objective number 3 is to analyze the effect of fully saturated and soaking in slope failure. So if you go for this one, you can see that the red one is Tazagi Formula 1936, and you can see the yellow one here, yellow come to this, and this one is Anderson, or we call it Magnor, the inventors, and Anderson 2003. So they come up with the yellow line graph, mean that's and then for the Tazagi is straight line, mean that one is straight line, another one is like this. We change the pen color first. So another one come like this. So this one come here straight, and then it curve. This one is parallel. This one is this straight line. So this two formulation, this theory, we apply and see what happened to our slope failure. Okay, so mean that is it the analysis is right or wrong? Okay, when you see this one, you can see that curve formula 2003 give you the factor of safety 6.97. Meanwhile, for the Tazagi 1936 still give you increase the high value of the plane surface about the shear strength model. Okay, so for the engineer normally for factor of safety you must get 1. It's less than 1, you can see that 0.9 or 0.8. It means that this one zone is slope fail. Slope already fail. But if you get the value 1 or above, so the slope is stable. Alright? But sometimes for the industry, they say that the factor of safety is 2, mean that from 2 to up, slope safe. 2 to below, the slope going to fail. Okay, this one normally for the academician, this one normally for the industry. Alright, so even though this one we can get 1 or 2, but you can see that this value is higher, is still safe, meaning that the slope not going to fail. The slope safe, not going to fail, or failure slope will happen. But you can see this one, this value is less than this value, mean that the new theory give a good signal if you consider many parameters. For example, that's about how you using, we call it no cohesions formula in the analysis. You can see that the value is going, the value factor of safety is going slightly lower. Alright, very interesting. And this one is high. Normally, the engineer or the practitioner using this one, they still using this one. Mean that sometimes our calculation maybe we should recheck. We should recheck. Okay. So slope height we lower it 20% to make it we call it not really critical, but what happened to the ground actually. And consider soil being soaked for the 7 days. And before that, after we are lowered down 20%, we check the stability of the fully saturation case. And we found out that the curved surface for the fully saturation we lowered at 20% is 2.85. This is our slope profile, new profile, we lowered 20%. And this one is the plane, we call it the plane to fill. Okay, and then you can see that the plane surface is 3.88. This one still lower, this one still high. So normally we have take this as a precaution. Okay, so after we soak for the 7 days, remember this theory, we have another one. First is Tarzagi 36, and there's a green one is from Maknor and Anderson. So this theory is come out to 03. Okay. And so what happened? We go to this one. Alright, you can see that curved surface give you 1.46 is near to the zone of fill, especially when you use factor of safety going to 2 for the industry ones, so remember that. And you can see that plane surface is going 4.15, 3 times higher than curved surface, and it shows that this one is stable, good, stable, is safe. But is it this slope safe or not safe? According to this value, we are not safe. According to this value, we are safe. That's why, according to one researcher, Osman, through his PhD in United Kingdom, he calculated about Tazaki formula using this parameter and see on site some of the calculations fail, on site is not fail. Sometimes they say the calculation is fail, they go to site is not fail. Sometimes they say it's safe, very good factor safety, they go to site the slope going to fail. And then through his findings, they are recommended him as a PhD in the United Kingdom. That is good. But here we can see that is a very danger because we're still using this one. We're not using this parameter. Okay, and it showed that to us that we are lowered 20%. We are lowered 20%. Alright. And we are working for 7 days. And more scenario, this calculation we infiltrate at 3 meter. So this is the result we get, 1 and 2. Alright. We are soaking 7 days. We lowered the original slope for 20% to make it safe. And we infiltrate around 3 meters. The rainfall come in, and then it penetrate 1 meter, 2 meter, 3 meter. Okay, so make it the worst scenario. And lastly, our overall conclusion saying that PSD, we already agree that 44% is gravel, and we agree the main contribution is sand, 36.7 is permeable, and makes the water pass through the soil. It's a permeable soil type. And we also have sand, more we call it, the case become worse because the sand also permeable and it's very hard and allow the water 18.66%. And lastly, we have clay is around 0.87%. Right. For the saturated shear strength behavior of the test has been determined as nonlinear failure. Yes, we can have one is nonlinear, another one is Tarzagi straight line. The transition shear strength is 85 kPa and corresponding transition effective strength is 150 kPa. And the effect of soaking for the test for 7 days and also the infiltration reduce the shear strength of soil. So you must understand this one. And number 3, slope stable before infiltration with factor of safety of 3.0 and 6.97 according to nonlinear failure envelope. Right? And consider a prolonged rainfall for 7 days, then the slope fill cross section. Moreover, the event when being infiltrated 3 meters depth. This analysis explains how the slope has suffered from a consistent failure in effect of prolonged rainfall, mean that soaking and infiltration. Right? And in recommendation, lastly, we should consider infiltrations and soaking in the slope design until to construction stage to make sure our slope calculations is on the right track. So by that, thank you very much, especially to the conference, or we call it the crew for this conference, International Conference of Trends in Technology, Business, Education and Social Research, ICCTBER, BESR 2020 is under Kaizen Renovation Center from Tanjung Malik, Perak. Again, thank you so very much to Dr. Fazli and team to make this international conference happen. Thank you. And my paper today is show to you that we are practicing the wrong calculations in our analysis and design of slope failure. It's become danger for us. Thank you, everybody. Assalamualaikum and see you again.